So here's an example. So here's an equation. That's going to be over the domain from x equals 0 to 1 with the initial with u at 0 equal to 0 and u at 1 equal to 0. So two essential boundary conditions. All right. Now we can develop the weak form for that. There's a three-step process. I won't do it. I'm just going to write down the weak form, but let's remember what the three steps are. Step 1. Yeah. Multiply by a weight. Move everything to one side of the equation and multiply by a weight function. Step 2.
Integrate over the domain.
And
Or the interior.
integrate over the body and integrate by parts to shift some of the differentiation off onto the test function, right? And then step 3, compound the boundary condition. That's it. So if we do that, the weak form is that, and I've written it in such a way that I've grouped the terms that involve del u and u and the terms that only involve del u. All right? So with that, my quadratic functional becomes that. All right. So then I'm going to substitute in my approximate solution, and I'm going to use C1 times x 1 minus x plus C2 x squared 1 minus x plus C3 x cubed 1 minus x. All right. Remember last time we said that these have to be linearly independent, right? So it's clear they are. Right? So this y multiplied by x and multiplied by x again. So they are linearly independent, all right? So then I have the three unknowns. Once I substitute my approximating function, substitute this into that, and integrate, then I just have the only unknowns are the c's, and then I can just use the techniques from ordinary calculus. So I just have an equation like this, another one like that, and another one like that. All right, so let's do it. I'm gonna do it in Mathematica. So I have u of x equal, can you guys see that? Can you make it a little small? Is that okay? Okay. So so u of x is C1 x 1 minus x plus c2 x squared 1 minus x plus c3 x cubed minus x. Okay, so then my quadratic functional is 1/2 the integral from 0 to 1 u prime x, so that's the first derivative of u with respect to x, squared minus u squared plus 2x squared u of x dx. All right, and this is one reason I like to use Mathematica in class, because you don't have to understand the syntax. I can make an integral and it looks just like an integral, right? So you don't have to understand some cryptic syntax if I was using some other language, right? Okay, what happened? There we go. That should work. Okay, so Mathematica performed the integration for me, so now you see it's just a function of the c's, right? So then I can make three equations. Equation 1 is equal to d I c1, and that's equal to 0. So there's one equation. So taking the derivative with respect to so now I have my three equations. And you see these are just linear in the unknowns now. So I can set up a linear system, solve that guy. So solve equation 1, equation 2, equation 3 for the unknowns. So there's my solution. So then I can plot that. So there's my approximate solution to the differential equation. All right. So that's an example of using Ritz method. Both last time when I used the sort of generic weighted integrals method, which turned out to be, if you really want to classify it, a Petrov-Galerkin method, and this time when I use Ritz method, I didn't give you any clue of how we choose these interpolating functions, other than I just said what the requirements are. I mean, they have to be linearly independent, and they have to satisfy the essential boundary conditions, right? But that still gives you a lot of freedom and choice of how you choose them, and sometimes that's a good thing. You can use some knowledge that you may have about the solution to pick something that works well, but it's very difficult to do in general. So what we really want is a more systematic way, right? And so let's talk about some requirements